subsidizes farming. If the government didn't provide farmers with subsidy funding, this particular country would not have been able to grow enough food to keep itself feeling secure in times of political conflict. But to subsidize farming, they had to figure out how much to give each farmer. And the rules around that subsidization were quite complicated. I was asked to come in and build a data model that they could then use to build applications to help manage the financial subsidies to all the farmers over time. And to do that, the data modeling process is you talk to a lot of people. You say, how does it work? What are the rules? In this example, the real world is on the far left, and it almost always seems to start with the real world, doesn't it? The real world was walls and fences and ditches and earth and areas where they were growing some crop, in this case, wheat. And the way that this agricultural subsidy government department looked at the world was the growth area where the actual plants were coming out of the ground was the agricultural parcel, but the fenced-in area was the reference parcel. And it got more complicated. The more you asked, the more details seemed to come out. For instance, it wasn't just about within the fence that mattered as the reference parcel, but two different farmers could be growing two different crops within that one fence. They called it the farmer's block 1 and the farmer's block 2 and the whole thing the physical block. I won't bore you with all these details, but as you dig in, you find out that it's not just the real world anymore. There's also invisible things like renting. How does it work if somebody's renting land from another farmer? Does the renter get the subsidy or does the owner get the subsidy? And what about variations on where the farmer lives versus where they should send the check, and the interplay of the land with the county and parish, and they could have this thing called holding boundaries. All of this played into the subsidies. How do you create a data model for that? Well, when you're encountering something like this as a data modeler, you buckle down. Maybe you consult your favorite data modeling book. Highly recommend Steve Hoberman's work. And you start building relational tables. At least this is the way it used to go. So maybe there's a place of business that someone talked to you about in subsidy farming, and it needs an ID and an address to identify it. Maybe there's a production unit that's defined by 3 different area descriptions, a county, a parish, and a holding. Maybe they're related to each other. So you've got a table that joins them up by combining their 2 keys and describes the connections with these funny crow's foot lines known as cardinality relations. And you eventually end up with a logical data model that is describing all the tables in your database and lines describing the relationships and cardinality between them. It's kind of beautiful in a way. It was my favorite part of any application development project. Now, this is for relational databases. How does this differ for a graph? We'll get to how a graph works in a minute, but for a graph, instead of tables and invisible relationships that need to be instantiated by SQL queries with joins at the time of writing the query, the graph database instantiates everything, the nodes and the relationships. And as you can see here, that same collection of place of business, production unit, and the join between them, the POB prod unit table, are represented by a production unit node type, a place of business node type, and an overseas relationship. And each of the nodes and the relationships, in some cases, have properties that make them unique in the database. So the name of the node, that place of business or production unit, is called the label. Overseas for the relationship is called the type, and all the little detailed data sets that go with them are called properties. This is called a property graph. So nodes, relationships, and properties. So let's take a look at a sample data set that explains this whole process that we're going to step through, which has really only 2 different node labels, person and beverage, and only a few relationships, 2 of which are called out here, married to and likes. So in this tiny example, it calls out one of the cool things about graph, which is even people people that don't know how to do anything with technical databases can read them like a newspaper. It's easy to see that Jane Doe, whose gender is female, was married to John Doe, whose gender is male, from 2010 to 2023. And it's easy to see that John Doe likes ginger ale, which costs 75 cents a can. You can read it like a newspaper. Sometimes people say the graph is like the whiteboard. When you're figuring all this stuff out on the whiteboard, drawing the circles and the arrows, it just translates straight into a graph. And as a long-time data modeler, I found it much easier to do than a relational design. How do you talk to this data? The language is not SQL, it's cipher. This is an example of the cipher for asking the question, how much would it cost? This is an example of the cipher. for asking the question, how much would it cost to buy Jane Doe's former husband a can of his favorite soft drink? And it's a really interesting language that uses sort of ASCII art to depict the nodes and the relationships in the query itself. You can see the parentheses around the person, match person, married to is the relation, and there's a little arrow that shows the direction of the relationship. There's other traditional stuff that you're all very familiar with, I'm sure, like SQL clauses like where and so on. But it is its own language. And the responses can either be another picture of a graph, which we'll see in a sec, or a traditional table response. Like in this case, the answer is the beverage is ginger ale and the cost is 75 cents. So before we get any further into the details of a graph, what are knowledge graphs? This is sort of where you go all in on some aspect of your business. And why would you want to? Here are some places where you might consider using a knowledge graph rather than a relational database or some other form of data store to hold key production data. Things like social networks, hierarchies, genealogy, a series of ingredients in a recipe, for instance, or a family tree. Routing and supply chain are also a popular one. Networks. People model their infrastructure with graphs sometimes. Anything to do with a linked sequence. I was talking to someone at the conference about the patient journey, where a person begins a journey in trying to figure out what their ailment might be, and meets with various technicians and nurses and doctors, and you sort of track that person's history and everything that happens to them along the way. Turns out that graphs are really good for that kind of use case. Or metrics. Graphs are helpful for taking a journey like that, for instance, and then attaching metrics along the way. For some reason, being able to have these sort of like tags along a sequence works very well in graph. And so does aggregation. If you're trying to express something in terms of what do we show to the shop floor level? What do we show to the manager level? What do we show to the C-suite level? The aggregations that are connected to the underlying data can be well modeled in a graph. Before I go on from this, we're going to be mostly technical from here on out. Are there any questions about why bother, or any of these use cases, or anyone who's got a great use case of their own? No? Well, please speak up anytime. Those questions are always welcome. All right, so what we're going to look at to test this all out is a toy graph with made-up data. And part of the reason I have made this data up is I originally did it with the royal family in England, and it actually created a with the real royal family people, their relationships, their children. And then I realized that the data in the LLM itself was influencing the results of all the questions that I might ask of this LLM with additional data. So I decided we'll do it with fake people, fake data, and that way the answers have to match or have to diverge from what's in this data set, and I'll know whether the LLM is being accurate or not. So what is this? It starts out with Adam Adams and Adele Adams, the patriarchs, who are married and had some kids, Angie and Brittany, who then married and had their own kids, and so on and so on. And at the end of this genealogical family tree, we have some of the beverage preferences of all the great grandkids. Belle and Ben and Brandon and Carl and Christy and so on. And part of the other plan for this is it's easy to tell if the graph is if the LLM gets the answers right or wrong, because most of the answers have the same first name if they're getting into the right generation. So that was part of the plan too. So let's see, how does it work? Well, first you load this data, and you can load data in a variety of ways. Like most software products, there's all kinds of ways to get data in and out. This is an example just in pure Python code where data is in the form of text, and you run it as a cipher statement that loads the data into an empty cipher database, or to an empty Neo4j database. If you wanted to see your data, there are browsers that allow you to look at a graph database and visualize not just the content.
司换一下。你们公司大多也是和你一样的用这样的电脑吗？
是，他们电脑应该会好一点。
你申请一下。你现在就申请，或者想起来的时候，我怕你想不起来，你申请一下。你可以录个屏，成没呀？成没呀？录个屏，拿手机拍。等它卡的时候，你看，你说要卡10秒，或者卡个5秒、3秒的，你看他们会不会帮你换？东西要拷出来，你知道吗？有些你经常用的Excel。罗阳不是笔电的吗？是吗？谁是笔电的？让他们帮你物色一下呗，可以吗？嗯。
Contents in text format, but in actual graphical nodes and edge relationship formats. And this is an actual graph database. If you wanted to see database, right? If they're getting into, well, that was part of the plan too. So let's see, how does it work? Well, first you load this data, and you can load data in a variety of ways. Like most software products, there's all kinds of ways to get data in and out. This is an example just in pure Python code where data is in the form of text, and you run it as a cipher statement that loads the data into an empty cipher database, or into an empty Neo4j database. If you wanted to see your data, there are browsers that allow you to look at a graph database and visualize not just the contents in text format, but in actual graphical node and edge relationship formats. And this is a snapshot from Neo4j's browser-based interface. As you can see, the married relationship between Chris bond and Connie bond is highlighted yellow, and that means on the right, it'll show the relationship properties. And you can see there are a couple of sort of inbuilt IDs, the element ID and the ID, but then the from and the to are data sets, properties that were intentionally put into the...
你已经那个了，买票了。
The data set for our purposes. So also this labels the specifics of each node, but the labels themselves could also be displayed instead. But we use color coding instead to get the fact that there are people and beverages in this picture. And you can see some of the other relationship labels: is father of, is mother of, and so on. So we talked about how do you query it. We use cipher, but what if, as we talked about, we wanted to be able to query it with a non-cipher natural language question? Hey, graph, how much would it cost to buy Jane's ex-husband a can of ginger ale? And chatting with a graph database requires help from an LLM because we don't know what the human language question will be. We need the LLM to interpret it. But LLMs work with sentences, and the graph is structured data. We're going to have to do something to turn that graph into sentences that an LLM could understand. And interestingly, graphs are kind of set up to hold subjects, verbs, and objects. Node, subject, relationship, verb, other node, object. So it's really easy to turn a graph into a collection of mini documents in a way. Here are in orange, you can see some of the ways that you might choose for this graph to turn the data into sentences.
Oh, interesting.
And here's the code for how to do it. It's a series of cipher queries that find the relevant nodes, turn them into regular sentences, and then store them in the place that you think they should live in the graph. And it ends up adding properties to each of those things. So whereas before we just had from and to for our married relationships, now we have a sentence property. And this
我操，牛逼！把 graph 变成 sentences。
In the middle one, Jane Doe is married to John Doe from 2010 to 2023. There's one last thing we have to do before we can set this up for business, and that is we have to add embeddings to our graph. Fortunately, Neo4j allows us to store that data format. So each of those sentences will be turned into an embedding. Now, what are sentence embeddings? It's too short of a talk to really get into that, so I'll just say a rough approximation is you're turning a natural language sentence into a series of numbers. Those numbers express vectors, and vectors can be compared for meaning, not just keywords.
些放了。
Word combinations, but meaning. So the three sentences shown in the middle of this slide: ginger ale is a sweet carbonated beverage that aids digestion. Pepsi's flavor profile includes caramel and citric acid. And my boss drank the Kool-Aid about AI agents. My boss did drink the Kool-Aid. Yeah. Hope yours didn't, but mine did. Which of those two are more similar than the third? I would say the first two, ginger ale and Pepsi, are talking about two drinks, whereas the reference to Kool-Aid in the third one is less about the Kool-Aid and more about the boss and AI agents. So the vector representations of those three sentences would bring the Pepsi sentence and the ginger ale sentence closer together, making them more similar from a meaning standpoint. And here's how it works. This is how you turn sentences into embeddings with a Python code that uses the sentence transformer called paraphrase, mini LM L6v2. It's pretty old. I used it because a friend said it was good, and it maps to a fairly small set of dimensions, just 384 dimensions of dense vector space. But it's a workhorse. It ran quickly, and we run it using Cypher again and store the results in the graph. And now what we used to have as a from and a to for that married relationship has become a from, a to, an embedding, and a sentence. So it's all in the graph. It's all ready to go in one place. Let's start using it. By the way, here's the code for the indexing. And a lot of this code I'm sharing just to show you that there's not much to it. It's pretty simple stuff. The cipher takes a while to figure out. You can figure it out in a couple of days, but the rest of it is pretty basic Python code. And just for note, you can see there the vector dimensions were 384, so you have to know what sentence embedder you're using, and you have to use that sentence embedding LLM for everything you do in this entire process, because the embeddings have to match. And then the similarity function we'll get to in a minute is cosine similarity. Other than that, it's pretty standard. So we prepared our knowledge graph. Let's get into it. We're going to ask a question. Embed it and try sentence similarity, semantic similarity. So what questions can we ask of this data? I came up with 9. From the first to the 9th are increasingly difficult setups for the LLM to answer. It starts out with simple stuff like who are Angie Bond's children? More difficult stuff, which of Bob Bond's marriages produced children and how many? And a really hard one at the end, Bob Bond is throwing a party exclusively for his grandchildren. First, identify who Bob's grandchildren are. Next, identify each grandkid's favorite beverage. If the grandkid is a boy, allocate him 5 cans of the beverage. If the grandkid is a girl, allocate her 10 cans of the beverage. Then produce a list of beverage types, counts, and costs. I mean, these aren't difficult things for you or I to do. But for the LLM, they represent some pretty challenging things given this data set. It's got to traverse a family tree. It's got to group things by a particular set of categories, and it's got to do math. And none of those things are particularly easy for LLMs, at least at the time I ran this. They are getting better all the time, but still, these are challenges. And it may be worth calling out that since doing this rapid prototype, MCP has become increasingly popular. I've experimented, I can't tell you much about it today, but I've experimented with giving the LLM a tool to allow it to traverse a graph. And using a graph makes traversal really easy. So that is another way to accomplish this, especially when the question might be pretty lengthy, if it would have to traverse 5, 10, 20, 25 different hops. I think MCP would be the way to go about it. This particular data set is small enough, so as you'll see, it didn't turn out to be a problem, but worth considering. So let's start. We've got our question. Now we'll do the sentence embedding. And the sentence embedding in Python is one line. It's really easy. Question embedding equals model and code question 9. Ollama makes this really simple. So we take that big question about Bob Bond and costing out the drinks, and we turn it into an embedding. So that's done. Now semantic similarity. Again, remember, this is where we're comparing embeddings to each other to see how close in meaning they are, not keywords. And what's the keyword distinction? For so long, before all the embedding stuff came along, keywords was the way to go. Remember fuzzy matching? With keywords, you'd say, I'm searching for my data, through my data for something to do with dogs. And you might get back anything that had dogs, doggy, dog food, sheepdog, but nothing about canines or Labradors, because they don't have DOG. And the keyword search would know nothing about relevance. You'd get back everything that matched, whether it was dog food or sheepdog. It's just everything that matches those characters. With semantic search, when you search for dog, the meaning gives you canine, puppy, man's best friend, all the dog breed names, and if it's sentences that you're looking for, it'll rank them by relevance. Because it's not just the match, it's how similar in meaning the search term is to the searched data. And that's amazing, isn't it? And you might wonder, what is the meaning of meaning? Here's a wonderful explanation from a Google research article called Advances in Semantic Textual Similarity. The top question, how are you, has all but one of the same words as the second question, how old are you? But they're very semantically different, right? Whereas the second question, how old are you, has no words in common with the third question, what is your age? But they're semantically very similar. And this Google article explains it's the answer to the question that helps you figure out how similar they are. If the answer is very similar, then the questions are very similar. So how old are you? I'm 20 years old. How are you? Great. Different. Versus how old are you? What is your age? Same answer.
有趣，宝贝，可以，还没搞好。啊，对，换一个电脑。 真行，你想吃啥？
你想吃什么？
你吃不吃浓心拉面？
宝宝。谢谢猪猪宝宝。
这不怎么了？
还好你陪我来了。我帮你买票。
我自己买。
我帮你买。
卡了吧？那我多赚你点钱。
不用了。
不用呀。
还好你陪我来了。还好我的生命里有你的存在。
那请你
好。
把 Excel
好。
托付给我，
好。
它解放你的脑子，
好。
让你彻底变成。
等我有空了，我给你讲讲我的经历就知道了。我请你吃饭。你吃什么？我请你吃。你要吃什么？我请你吃。
你的新电脑让公司 IT 帮你装一个 Python 可以吗？没有。
可以。我们应该有 Python。
我还要 Go， 帮我装好。
可以。但我感觉我的电脑有点慢。
换。拍个照给他们呀。勇哥看了都摇头。吃上吧，下吧。哎，要不要吃 biang biang 面吗？
这里没有方便面。
你想吃什么？泡泡粥吗？番茄粥。
吃不吃那个水煮肉片？
你们一直在心心念那玩意儿。
但是我吃那个水煮肉片，我拉肚子。
那一家是哪个家？水煮肉片那家。
长沙的。
What the fuck? Finally. I had a little revisit to fix the BHs. Interesting. No. Sign with Google and OK， 我们更新一下。Version control some shit. Manager.这怎么回事？不能 update。
他帮我点外卖了。
嗯。奇怪。前面有个东西，小红书的群可以加一下，可以送你一个语音转文字的软件，1年免费，1个月要$10。
要 VPN 吗？
应该不要，中国人搞的。看看啊，我先试用一下吧，好用我就给你弄一下，但是要你的小红书自己登进去。我的 Library Manager 怎么炸掉了？操！Advanced Panel Control 怎么 update 呀？我操！看看。 掉。哦，关掉。I don't know if that happened. If that works. Why? How about the bottom?
我点外卖了。你想吃什么？吃不吃那个吗？吃不吃水煮肉片吗？
可以。
我选一个水煮肉片，然后你再选另外一个。
好。
你选哪一个？再来看一下。
水煮肉片。我吃紫苏鱼杂。
不是吃过那个吗？你不是说那个鱼泡有点怪吗？
可以应该水煮肉片。清炒油麦菜没有？对吗？好。
你不是水煮肉片是吗？
我已经酱板鸭烧牛蛙要不要？
不要牛蛙。
这里还有螺丝。2个米饭是吧？杂粮饭要吗？
杂粮饭，我不要杂粮饭，我要大米饭。你要杂粮饭，你可以点。
要蒸蛋吗？
不太可以。
我觉得就这样，对吧？
杂粮饭吗？
不吃。我今天中午吃的稀饭就不是杂粮。
来一个呗。
不用
来一个那个，你
不用
是要吃蒸蛋吗？
不用。
宝宝，你是不想吃肉片是吧？是吗？
我都行，只是想试一下其他的。
我感觉这个好吃，就这样点吧。你吃馒头不？吃馒头啊。
你想吃吗？也行。
可以吃一个，我们俩吃一个吧。
可以。要吃吗？说回点啥呢？
个小撞红烧怎么吃呢？宝宝刷牙吗？刷牙吗？
我不刷，
刷吧。
你刷吧，刷吧。
我感觉晚上没刷牙好难受，不知道你为什么能忍住。
啊，我晚上刷了呀。
哦，是，我晚上没刷。你早点刷吧，我昨天晚上没刷牙，直接睡了。
Hello. I control. Shit. Interesting. 你好，这是我第一次使用语音输入，感觉太棒。好。Data Levin 的似乎性能非常强悍，它的一些 fork 中有哪些是大较多的？多了个控制，多了2个控制。
对了。
我操！应该不会吧？
太神奇了。
没有的。
发生什么事了？太神奇了。Hello, hello. Das kann schon da werden.
样。
在地上。
我没看到，没看到，宝宝。哦，可能在我头上面。
没说话了。
这样。这样。哦，可能在我这个衣服里面。完了没有？
编辑。What? What the fuck happens, dude?无语，很无语。
喂。
机器人历练呢，现在在送啊。
嗯，好，谢谢。
好，拜拜。
拜拜。
还可以删了吧？ 去。